multiplying monomials with the same base. All right, so let me just off on the top here, just kind of jot down the general structure of a monomial. So if we say a times b to the c, a is the coefficient, b is the base, c is the exponent. All right. So when they're saying that an exponent or exponential has the same base, it's the thing that's being raised to the power. All right. That's what they mean by the base. A little warm. All right. So when I want to take something like 3 to the second times 3 to the third, I mean, I could throw that into a calculator, get an answer pretty quickly. But when we mix in variables, things start to fall apart that way. So we want to make sure we have the technique down so that when we do come against variables, as you can see in the problems below, we're ready for them. All right. So what we're actually doing when we're multiplying exponential expressions is we're really just replicating the value according to the number assigned in the exponent. So 3 to the second is the same as 3 times 3. 3 to the third is the same as 3 times 3 times 3. All right. That's beneficial to know because with that expansion, we get the sum total of the number of 3's that make up the product. All right. So I have a total of 5 3's, which could also be represented as 3 to the 5th power. All right. So another way I can look at this would be to say, all right, well, if I have a power of 2 and a power of 3, and each one of those bases gets represented twice for the power of 2, each one of those base or the other base gets represented 3 times for the power of 3, and all I'm doing is totaling out the exponent, couldn't I have just added the 2 exponents to begin with? 2 plus 3 gives us 5. It seems to make sense. All right. So in number 2, we try that technique. I would think that my answer would be 5 to the 6th power. That I would just add those exponents. But if you're not sure, we would say, all right, well, 5 to the 4th really means 5 replicated 4 times. 5 to the 2nd means that 5 is replicated another 2 times. And in the end, I have a total of 6 5's. If I count them up, 1, 2, 3, 4, 5, 6 of those 5's. All right. So then I would look at it for number 3, y to the third and y. Well, by the same rationale, I would say y to the third means y is happening 3 times. But then I'm multiplying it by another y. That second y, can be thought of as y to the 1st power. All right, so that's just one of those y's. But in the end, it looks like I have a total of 4 y's being multiplied, so y to the 4th power, which is what I would have gotten if I took my 2 exponents, 3 and 1, and added them together. All right. So then you look at a situation that involves some coefficients. 2a to the 2nd times 3a to the 7th. All right, so I could look at this and really just say 2 times, well, a to the 2nd is a pair of a's. 3a to the 7th, that would be times 3, and then 7 of those a's. So 1, 2, 3, 4, 5, 6, 7, all multiplied. But the commutative property tells me that I can multiply these numbers in any order I want. So why not multiply the 2 and the 3 first, get a result of 6, and then worry about the a's and how many of those there are. All right. So looking at the a's, I see I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of those a's, so a to the 9th. Now, listing out the expansion is not practical because if I were to do that every time, especially looking at the next example, x to the 20th, x to the 40th, I don't want to write out the x 20 times. I definitely don't want to write it out 40 times. So the shortcut is really necessary. But what we get out of this is that we didn't really need to do any of this work if we recognize that all I'm doing is multiplying the coefficients 2 times 3 to give me the 6. And then I'm adding the exponents. 2 plus 7 gives me the 9. So for number 5, it really is just a matter of taking that 20, adding to it the 40, and you get x to the 60th. All right, so when multiplying monomials with the same base, you just add the exponents. All right, keep the base, add the exponents. I misjudged how big that line was, so keep the base and add the exponents. That's all you're doing there. The numerical values, the coefficients, they work themselves out. You just multiply them together. Now, when you're raising a power to a power, it's a little bit different, but it's based off the same fundamental idea. All right, so power to a power, like for example, 2 to the 3rd raised to the 4th, is just telling us to take the 2 to the 3rd, multiply it by itself a total of 4 times. So you get 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd, which brings us back to this rule, which is keep the base, add the exponents. All right, so if I add all these exponents, 3 plus 3 plus 3 plus 3, that'll give me a 12. However, if you're adding like values repeatedly, that's the definition of multiplication. All right, so if I take the number 5 and add it to itself 5 times, the 5 times part of it is your clue that that's actually multiplication. 5 times 5. 5 plus 5 plus 5 plus 5 plus 5 is 5 times added. 5 times 5 is the shorthand way of saying that, which is 25, multiplication. All right. So, long story short, too late. 3 times 4 would have got you to 12 in one shot without doing any of the stuff in the middle. All right. Same idea for the second example. I would say x to the 4th squared would be x to the 4th times x to the 4th. I can keep the base, add the exponents, which would give me x to the 8th, but I could have just did 4 times 2 to get there in one shot. It only gets kind of weird when you incorporate multiple variables and then multiple variables with multiple constants or coefficients, sums and differences. That's when things get complicated. So right now, each individual concept should seem pretty easy, pretty basic. But when you start mixing it all together, that's when things get a little crazy. Right? So in number 8, x squared y raised to the 3rd, we could write that as x squared y, x squared y, x squared y. Each one of those y's has an understood exponent of 1. Whenever you write two letters adjacent to one another, there's an implied multiplication there. So if I say something like AB, like if I write AB, I'm really trying to say A times B. I'm just not writing the multiplication symbol. So each one of these has an assumed multiplication in there. All right, so what that gives me license to do is move everything around and group it in any way I want, because multiplication is commutative. Like my a Tom Marvolo riddle approach to things. All right, but that would be saying, all right, keep the base, add the exponents for just the x's. Keep the base, add the exponents for just the y's. So I would end up with x to the sixth, 2 plus 2 plus 2, y to the third, 1 plus 1 plus 1. However, just going back to what we started with, I could have said 2 times 3 gives me the 6. That understood power of 1 for the y multiplied by the 3 gives me the 3. So what this tells me is that for each factor in the base of an exponential that's raised to a power, I would multiply the exponents of each one of those factors to that power, or by that power, right? So like the next one, I'm looking at 2 times x to the third. That's really 2 to the first times x to the third, all raised to the fifth. So I have 2 factors in here. One factor is the 2 to the first. The other factor is x to the third. So take my 1, multiply it by the 5, so 2 to the fifth. Take my x to the third, raise that to the fifth by multiplying the 3 by the 5. So that's going to be x to the 15th. The only thing that you'd have to do additionally here is figure out what 2 to the fifth is, but powers of 2 are pretty easy. All right, so 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 gets you to 32. So you're just doubling over and over again. You know, if I had to do 2 to the 8th power, start off with 32, we know that's 2 to the 5th, double it, 64, double it, 128, double it, 256, that gets you to 2 to the 8th power. All right. So 32 x to the 15th. You can always just default to plopping it into your calculator, but it, yeah, there's the fun in that. It's like, I'm really good at math. And then they're like, okay, cool. You're really good at math? What's 37 times 15? And you're like, okay, I'm really good at math. Where's my calculator? Let me figure out 37 times 15. Like, I don't know that you're that good at math if you're always going to the calculator. Yeah. Just a thought. So, -2 raised to the first, a to the third, b to the fourth. And again, I'm only writing that -2 to the first power because there was no power indicated for it. But that whole expression is raised to the third power. All right, so right on down the line, multiply each of the powers inside by the power on the outside, and just really kind of log your result over on the right-hand side. So -2 to the third, three times 3 is going to give you a 9, so a to the 9th. 4 times 3 is going to give you 12, so b to the 12th. The only thing that we would need to do here is figure out what -2 to the third power is. So -2 times -2, 2 negatives give you a positive, so +4. +4 times -2, right? +4, -2, positive times negative is negative, 4 times 2 is 8, so -8. All right, so -8, squeaky chair, a to the 9th, b to the 12th. All right, So the shortcut here is just multiply your exponents. But as you could see from some of these examples, there's a lot more to it than that in some of these cases. So x to the 80th, when raising a power to a power, you multiply the exponents. Right. I wanted to take you through a few more examples because I don't want to kind of leave you off by doing all the easy ones and then let you struggle with the tricky ones. So on page 9, you have the rule there. Again, it's just a recap. When multiplying monomials, keep the base, add the exponents. All right, we'll do number 16 together. The other class asked me to do a couple of problems, so I'll do those with you too. Maybe they got jammed up on them, so I figured it's probably a good idea. All right, but this one's pretty spicy looking, I'd say. So keep the base, add the exponents, but it's like, all right, well, which exponents get added? You know, this is nuts. All right, what I like to do as a strategy is first deal with the coefficients, take care of the coefficients. If there are any exponents outside the parentheses, I'd handle those too, but that's not the case here. All right, so I can jump right into the idea of multiplying the 8 by the 3 by the 3/4. 8 by negative 3 by 3/4. So 8 times negative 3 is negative 24. Multiplying by 3/4 is the same as, well, it's two things. You can multiply by 3 and divide by 4. Whenever you multiply by a fraction, you multiply by the top number, divide by the bottom. Or you can go the other way around, divide by the bottom number, multiply by the top number. So I have negative 24 already. Divide that by 4 gives me a negative 6. Multiply by a positive 3 gives me a negative 18. Or you could put it into the calculator. I have it right here. But yeah, give it a shot first. You know, little brain exercise. All right. Now, when you're dealing with the variables, go in alphabetical order. All right, so x comes before y, so let's handle that. Now, I notice here that I have an x that's just without an exponent. There's always an understood exponent of 1, so I'm just going to chuck that in there. So I have x to the second, x to the first. Keep the base, add the exponents, x to the third. The only thing left are the y's. So I have y to the third, y to the second, y to the fourth. Keep the bases, add the exponents. 3 plus 2 is 5, plus another 4 is 9. So y to the 9th. Ah, that moved on me. And that's really it for this kind of problem because, you know, I used the color coding system so I didn't have to write too many steps. You don't have to color code it. You don't have to break out the highlighters, but you should have some sort of organizational strategy. To keep it all straight in your mind without much experience with this is kind of tricky, but it is doable, but you need practice, which is where the experience comes into play. All right. Power to a power, you multiply the exponents. So I wanted to do number 20. All right, because this is kind of a combo problem. We have powers to powers, but then we have a next step that we'll have to follow after that. So the first step is actually pretty easy. The first step is to take my 5 and multiply it by the 2, which will give me a 10, so v to the 10th. Three times 4 gives me a 12. Power to a power, you multiply the exponents. But now it's not power to a power anymore. We're multiplying exponential expressions. So now it's a keep the base, add the exponents. So the first step here was multiply exponents. But now we have to add the exponents. So v to the 22nd power. I'm just going to try to make as much of this visible as possible. So it was multiply the exponents first, then add the exponents. So 5 times the 2 gave us the 10, 3 times the 4 gave us the 12, but then we had to take that 10 and the 12 and add them together. All right, so now we're going to spice it up a little bit. Going down to, on page 10, the rule. I'll do that first, and then I'll take you through the spicy example, which is number 29. Scary stuff. When raising any expression to the 0 power, the result is 1. So no matter how complicated the expression is, it could be the craziest looking expression. If it's raised to the 0th power, the result is going to be equal to 1. So number 29 is pretty crazy looking, but if you look carefully, you see that right in the heart of it, that middle expression there, this guy right here, actually the thing that makes it look craziest is an expression that's raised to the 0th power. So this is actually going to cancel out to a 1. That's equal to a 1, which makes it irrelevant. All right, going back to number 27, look how crazy this one looks, but it's raised to the 0th power, so the result is equal to 1. All right, so there's not really much to do there. I mean, there's nothing to do. That one's already done. All right, but 29 has other stuff going on that we have to handle. All right. So first, I mean, PEMDAS is still a thing, order of operations, parentheses, exponents, all that good stuff. So, well, there's parentheses everywhere. We really can't do too much inside each set of parentheses, but what we can do is handle the exponents. This n could be thought of as an n to the first. This y could be thought of as a y to the first. Power to a power. So we multiply the exponents. So the 1 gets multiplied by the 3. The other one gets multiplied by the 3. So n to the third, y to the third. This expression is not raised to a power, at least on the outside of the parentheses. So the best I could do is just rewrite this one. So it's negative 2. I could write it as negative 2 to the first, but there's no other coefficients, so I'm not really worried about that. All right, negative 2, n to the 6th, y to the 5th is going to get multiplied by, well, there's really an assumed 1 in front of the n to the third, y to the third. So I can, just so I have a partner for the negative 2, I could put that 1 there. Negative 2 times 1, negative 2. N to the 6th times n to the third, keep the base, add the exponent. So n to the 9th. Y to the 5th, y to the third, keep the base, add the exponents, n to the, y to the 8th. All right. All made a whole lot easier based on the fact that that middle expression canceled away to just a 1. All right. And that 1 doesn't factor into the solution in any way, because if I take this answer and multiply by 1, 1 is a multiplicative identity. It doesn't change anything. All right. Then on page 11, somebody had asked about, I think it was number 12. Yeah, I'm pretty sure it was number 12 on page 11. So this one's got a lot of stuff going on, but we can assume a power of 1 for both x and y here. That negative 4 is really negative 4 to the first power. x to the first, y to the first, the whole thing being raised to the third power. We have a negative 2 to the first, x to the second, that whole thing raised to the third power. So we have power to a power in both cases. So 1 times 3, so negative 4 to the third power. 1 times 3, so x to the third power. 1 times 3, so y to the third power, times 1 times 3, negative 2 is going to be now to the third power, 2 times 3, x to the sixth power. Numerically, we'd have to evaluate the negative 4 to the third. That's going to be negative 64. Negative 4 times negative 4 is 16. 16 times 4 is 64, but it's multiplied by a negative. All right. This one we already figured out is negative 8 from previous problem. We have x to the third, y to the third, x to the sixth. So I'd multiply the 64, negative 64 times negative 8, which is going to become positive because two negatives make a positive. All right. So I would just take that 64 and multiply it by 8. 6 times 8 is 48, so 480, plus another 32. 4 times 8, 32, gives you 512. Keep the base, add the exponents. X to the ninth. Nothing goes along, there's nothing to pair with the y to the third, so that just comes along for the ride. And that would be our solution there.